Hello, my name is Uchenna Blessed Ochije. I am the team lead for the Robotics Team A at the University of Stavanger. For this year's competition, our team comprises of a total of 9 members, with 5 members as key members and 4 supporting members. For the 5 key members, we have myself, Uchenna Blessed Ochije, Mohammed Suleiman, Haman Hansel Yola, we have Alden, and we have Axel Johansen. For the supporting key members, we have Aber Kazi, we have Mohammed Amin, we have Luis, and we have Diego Solano. We are supervised by Professor Dansui.
Here is the flowchart. Here is the flowchart for our system. Simulation is running in the Open Labs, and then we have a device that is connected with the Open Labs to get all the values from the simulation. We are using our Python code to access the values and then store them in the form of Panda data frame from device, and everything is being done in real time. Then we are using the values from this Panda data frame to plot the values in real time in different graphs. Using these values, kick is detected in real time and warning is given. After the warning, kick is being confirmed prior to initialize the well control module. In well control module, we are using 2 different systems to control the well. One is MPD. We are changing the values of MPD choke from 0 to 1, and these values are then sent back to device, and in return it's being sent to Open Labs for changing the simulation results. The other method is controlling the kick using the BOP. For that, we are actually stopping the drilling before we actually close the BOP. So this is the flowchart for our system.
Hi, my name is Audun. I am key member and I will explain what Divis is. Divis is a versatile system designed to acquire and transmit live drilling data from multiple sources, including digital twins or real-time rigs. It enables the automated analysis and control of drilling operations. The key benefits of Divis is that it enhances safety. Divis uses isolation tools to maintain formation pressure isolation, reducing blowouts and drilling-induced hazards. Improves efficiency. Continual process significantly reduces non-productive time. It's cost-effective, combines multiple steps, reducing time and operational costs. It allows extended reach, potential to access reserves that would otherwise be unreachable. Below is a step-by-step guide to activate and connect TVs together. First, set up Docker Desktop and CMD. First, open Docker Desktop, open CMD, initiate connection with Docker Hub. Visit Docker Hub link. Input the provided code into CMD. To access OpenLab, open a new browser page and navigate to localhost link. The last step, UI Expert installation and configuration. Download and then open UI Expert. Under Server, select Add Server, then Custom Discovery. For reading, input localhost 48030. For editing, input localhost 48031. Select and connect to the server. You can then drag desired parameters to the data access view or double-click for attribute ID. This ID will be used in our Python system to transfer data and commands between drilling simulator like OpenLabs. To change these values, use localhost 48031. A last note is that Divis uses SI units and OpenLab uses other units, so have to be careful. Also, some units can be positive in OpenLab and negative in Divis, like top of spring speed.
Yes, hello, my name is Axel and I'm responsible for the kick detection part. I will take you through how we plot and visualize the data and also how we do kick detection. There's 2 parts to it. There's one part of visualizing what's happening and one part of letting the well control script know. So I'll take you through this kick detection flowchart, and it starts by us retrieving data every second, as you can see all the way on the left. From this, we can then plot the linear regression, visualize by adding the color spans, and we could also do kick detection based on the trend of the line. And I will talk a little bit more about that later. But this is all sent to the plotting script, so we can visualize it. I will show you also how that's going to look later. And then we also let the well control script know what's going on. So this is how things will look like, the different parameters. We have green and red spans plotted in real time and stored on the plot, so they will tell us something about the trend and where it's going. Green is for up, red is for down. There's also a yellow line, as you can see, and that's a straight linear prediction line that tells us something about the trend, the current trend, and where the line is going. This is really helpful for letting the driller know if a slight change in the current trend is going to break the threshold or not. Yes, and you might be wondering what those thresholds are. Well, if you look at the red lines, it tells us that this is the 5% average of the past 100, the average of the past 100 time steps, and 5% of that, I mean. I will show you more about how we calculated those later. But essentially, this gives us a great overview of how the data has been and is looking, and that's what we need. So you might be wondering, how is a kick detected? And when a value breaks the threshold line, that's when a kick is detected, and it's the current value only. The threshold lines are defined by plus minus 5% of the past 100 seconds, like I was trying to say earlier. These are adjustable, as we will need to fine-tune this, as we don't want to trip the kick alarm when we don't intend so. The prediction line will let us know when the trend is going off the path, and here's the formula for that. Simple y equals ax plus b, and it's from the previous time step to the current one. The prediction line is 100 seconds long. This is also adjustable. It's simply an assisting tool for the driller, so he can more easily keep track of where the trend is going. There is a cooldown system on these alarms, because it's constantly nagging the user that yeah, you're actually experiencing a kick now, and it's on 20 seconds. Color spans, like you saw earlier, have a simple polynomial filter applied to them, meaning that if the values are around the 0 mark, it'll smooth out the line, and this just helps with flickering, because if you're hovering around that flat value, it will flick between green and red. This is all done every second. I'll go back here so you can see it one more time, and this hopefully gives the driller a better understanding of what's going on in the well, and or with any given values he's trying to understand the trend of.
Alright, my name is Blessed, and I'll be speaking on trend extraction and analysis. So the reason for this slide is to throw more light on my teammate's work, Axel, who's worked on kick detection using trend analysis. If you can look at this result, you see a chart that shows ROP against time, and ROP because my thesis is based on ROP optimization, and the methodology used is the qualitative trend analysis method. So basically, this shows a proper classification of rising, falling, and stationary trends. The rising is colored in green, falling colored in red, and then the stationary in blue. But the most important part of this work is the change rate, because it's the vertical line that guides the driller, to know how much he has crossed the threshold. Alright, so change rate basically represents a change in y-axis divided by a change in x-axis, which is the time, and multiplied by 100. And the threshold, when the change rate exceeds the threshold, the driller gets notified, and then an action is taken. And in as much as my thesis was based on ROP optimization, it's also applicable to kick detection, especially if you are using parameters like the pit volume, or we're trying to consider the bottom hole pressure. And I would like to explain how the moving window is applied to trend analysis. First, we develop a polynomial regression model and then identify the trend change points. We continue to calculate the cumulative error to confirm if it's a change point or not, or if it is an outlier. Then we update the datasets. We also try to mark all the change points from the datasets that have been analyzed, and then we extract the trends. What that means is that we save each change point according to their nature, if it's increase, decrease, or stationary. And then we move on to apply the moving window for the same datasets, and then we continue this until all the datasets have been analyzed, and then we terminate the algorithm. For this task, we made use of the managed pressure drilling technique for our well control, which employs an engineered approach to maintain wellbore pressures within a narrow window margin, unlike traditional drilling methods that usually rely on mud weight to control formation pressures. The blowout preventer, that's BOP, is usually kept in place and operational, ready to be activated if necessary. The MPD, managed pressure drilling, focuses on the management of wellbore pressures within a controlled window, while the BOP, blowout preventer, serves as the ultimate safeguard in case of a well-controlled emergency.
Herman. Hi, my name is Herman, and this part is going to be about bottom pressure prediction. By leveraging machine learning techniques, we have successfully developed a predictive model for bottom pressure. This advancement indirectly enhances the critical task of kick detection during drilling operations. During our project, we experimented with various machine learning models, including random forest, XGBoost, AdaBoost, and LSTM. These models were designed to recognize patterns and relationships between various drilling parameters and bottom pressure. Once these models are adequately trained and tested, they can predict bottom pressure deviations in real time, acting as an early warning system for potential kick or losses. For automatic kick detection and well control, accurately predicting bottom pressure is crucial. Any changes from predicted bottom pressure could mean there's either an unwanted influx or loss of fluids. Our models can detect these changes and alert us, giving us more time to react and manage the situation. Among the models we evaluated, from the XGBoost, AdaBoost, Random Forest, and LSTM, the LSTM model stood out as the most accurate for predicting bottom pressure. This was further proven in an online test scenario, where the LSTM model was able to successfully predict bottom pressure even when kick parameters were unknown. As you see in the figure 5.8 to the right, it's an online test of the LSTM model. And after around 250 seconds, the actual drilling starts, and that's the part of the model that actually matters. And you see that the red prediction line is predicting really, really good. So this showcases the efficiency of our LSTM model for real-time kick detection and well control. Its integration boosts potential for early kick detection. In addition to selecting the best machine learning model, it was equally important to identify the key features that influence the bottom pressure. Using sensitivity analysis, we identified main pit density, rate of penetration, flow rate out, standby pressure, and weight on bit as key predictors of bottom pressure. Furthermore, through recursive future elimination, or RFE, we understood the importance of future selection for improving model accuracy. Understanding future importance helped fine-tune and understand our machine learning models for better performance and the sensitivity from the input parameters to the outputs. Thus, these more accurate models contribute to improved kick loss detection and well control.
Here are the files that we developed for our system. The simulation is running in Open Labs, and then we have our main PI that is being connected to DVIS, and then DVIS is in return connected to Open Labs simulation. So in our main PI, we have all the parameters defined that are you can see on the right hand side. For example, we can get the values, all these values from the DVIS, like pit density, pit temperature, pit volume, but we will not be using all of them in our system, but we can actually get all of them. Of course, it depends on the DVIS system, like what values we are getting, but right now we can get all these values from DVIS if the user wants. So in the main PI, we will be defining those ones and then getting the real-time values for these parameters, and using some of those parameters we will be using the trend.py and then prediction.py to check if there is a kick or not, and using that one we will be controlling the well by using well control.py, and at the end, if well is controlled, we will be resume the drilling using the well control.py module as well. All these data can be and will be saved in our main data frame, and then we will be using the 4 parameters that we actually can set in DVIS. Two of them are very important one, like one is MPD choke opening and the other one is BOP choke opening. So we will mainly be using these 2 parameters to play with and then controlling the kick. Other parameters that we can change are flow rate in, RPM and string velocity, and we will be using these parameters as well to stop the drilling or increase the ECD in some cases.
It has indeed been an interesting journey for this year's robotics competition, and I'll like to take our time to discuss the outcomes of this year's task. We have a total of 4 students who ended up writing their master thesis in line with this year's competition and supervised by Professor Dan Sui. For the bachelor's thesis, we have Axel Johansen, who worked on data-driven approach for kick detection and trend analysis in drilling operations. We also have Hansel Yola, who worked on data-driven bottom hole pressure prediction during normal drilling and kick. For the master's thesis, we have Mohammed Suleiman, who worked on autonomous well trajectory design considering the limitation of torque and drag forces. And myself, Uchenna Blessed Ochije, I did my work on automated real-time radar penetration optimization using trend and dynamic analysis in drilling operations. We were privileged to attend some SPE conferences. We also had some companies visit us at the university. We had some trips to some companies as well. And for the SPE conferences, we had the IADC, we had ISC, WSA, and the University of Stavanger Energy Day, all of which happened here in Stavanger, Norway. We had visits from NOV, we had Well ID, we had Ulrig and Halliburton visiting us here at the university, checking out our simulation lab and the physical rig. We also had some team bonding events and entertained students from the Technical University of Clausthal, Germany, who visited us here in Stavanger and got to experience the culture, the food, and also some company trips. And we were interviewed by David Gibson. Gibson reports from the US. And some of our team members were awardees of some special awards to appreciate the milestone they've achieved this semester. One of such is Mohammed Suleiman, who was awarded with the Best Master Student Award 2023 by Techna and the Society of Petroleum Engineers. And during the Energy Day at the University of Stavanger this year, Axel, Haman, and Blessed were all awarded Best Poster Awards respectively. It's been an interesting journey, of course, and in such competition as robotics, it has sharpened our skills in different levels. For instance, we have learned how to work in a multidisciplinary project. And also, it has also developed our programming skills and the ability to solve complex problems, especially the ones we didn't expect. And yes, getting to know how to work with DWIS has also been a highlight of this year's competition. And during this process, we were encountered with several challenges. The major one was getting to understand how DWIS system works, because we encountered a lot of bugs in the system, and we couldn't establish a stable connection. And we were able to reach out to the developers, and we were happy that we were assisted accordingly. And we also noticed that we did not have enough or available user case guide for us to learn from in terms of utilizing the DOE system, and the documentation for establishing connection is not sufficient for the students to get to understand how the DOE system works. For future work, we would like to see a direct connection between the DOEs and the Open Lab Drilling Simulator, such that we can access or send and receive data from the DOEs to the Open Lab and vice versa. And we also like to use a more advanced regression model for the trend analysis, unlike what we used for Axel's work, which was a linear regression. We feel like we can get more detail from the trend analysis if we utilize a more advanced regression model. I wouldn't like to end this session without acknowledging some significant individuals who have contributed to our journey this year. At the University of Stavanger, Professor Dan, Mr. Norbert, Sindre, who is the team lead for Robotics Team B, Physical Rig, and Professor Shell Curry. And for the Norwegian Research Center, Mr. Yana, Mr. Benoit, and at NOV, Jonathan James Carney, and of course, Gibson's reports, Mr. David Gibson. We appreciate your support for us throughout this journey, and we want to say thank you. On behalf of myself and the team, we would like to say thank you. And in wrapping up this session, I'd like to say it's been an eye-opener, it's been an eventful year, having to combine the tasks for this year's competition alongside our academics at the University of Stavanger. It hasn't been easy, but through teamwork, good supervision, good guidance by our supervisor, Professor Dansui, we've been able to achieve as much as we possibly can. And I must say that we have indeed developed both as professionals, as students, yes, and we look forward to the next stage in this competition. Thank you.